cycle, urea cycle. And one thing I want to do before we really get into the cycle is talk about what we've seen so far, and probably what you've seen so far in your metabolic pathways that you've seen up to this point, which is probably glycolysis. You've seen some in the pentophosphate pathway, the TCA cycle, beta oxidation. But you've seen sort of the end product of metabolism. And the end products of metabolism that you've seen up to this point, you've seen carbon dioxide as one end product. Another end product is water. But let's think about this also. Where have we seen loss of carbon dioxide? Well, number one, in the pentose phosphate pathway, we saw that in 6-phosphogluconate dehydrogenase, right? We saw it there. We've also seen it in pyruvate dehydrogenase. We've also seen it in two other enzymes in the TCA cycle, which were isocitrate dehydrogenase and alpha-ketoglutarate dehydrogenase, right? So those were reactions that produce CO2. We also have reactions that produce water. The main one we've seen at this point, phenolase, right? In glycolysis, phenolase produces water, okay? And there are many other reactions that do this. If you've seen the electron transport chain video, you've seen that, if you know anything about it. Also, cytochrome deoxidase produces water. So these are two of our end products of metabolism. But there's a third that we really only see when we're talking about metabolism of amino acids, and that is ammonia, or ammonia to physiological pH. Usually I'll just call it ammonia, because that's usually what they term it in textbooks. So we'll call it ammonia, although note that at physiological pH it is ammonium. Okay? And ammonia is the third main end product of metabolism. And by the way, these are basically waste products. Although water and ammonia and to an extent carbon dioxide are used in some reactions, they're mainly just considered waste products. Okay? And there's several ways that we get ammonia. Number one, there's two reactions that we talked about in previous videos. One was the reaction of glutaminase, and that's the reaction that I had labeled glutamate A. That's the reaction where we take glutamine and we deaminate it to make glutamate, and we get, of course, in the process we generate ammonia. And then we can take that glutamate further and use glutamate dehydrogenase to get it to alpha-ketoglutarate and ammonia. Okay, so these are two ways that we can get ammonia that we've seen up to this point. And by the way, both of these reactions are mitochondrial. So these reactions, these two reactions A and D that I'm talking about, they both occur in the mitochondria. Okay? Now, there are various other reactions that we'll see throughout our journey in amino acid metabolism that also produce ammonia. So when we do amino acid metabolism, we're creating a lot of ammonia. And that's something to keep in mind. When we do amino acid degradation, we are producing ammonia. Okay? And one thing you should be aware of is that ammonia is, at least in large amounts, is not good for cells. In fact, it's toxic. It's especially toxic to brain cells, and certainly you don't want your brain cells to suffer. So your body has to have a way of dealing with excess ammonia, which is going to be prevalent under two conditions. And by the way, some teachers or professors will have you learn things in terms of like fasting or bed state. What I like to do more often is instead look at like what we have in the blood, right? So let's say that we're in the fasting state. Okay, let's say that we're in starvation. In other words, let's say we haven't eaten in a while. Okay, let's say we haven't eaten in a while. Well, you can imagine several things. Number one, our stores of acetyl-CoA, ATP, NADH, all of those things that are present, after we eat, those things are going to be low. So we're going to have low acetyl-CoA, low NADH, low ATP. All those things are going to be low. And you can also imagine that we're going to have high ATP, high AMP, high inorganic phosphate, things like that. Things that are associated with low energy. Those are the things that are going to be high in the blood, or excuse me, high in the cells, excuse me. Now here's the question. If we are in the fasting state, if we are there, what are we going to get? Well, how are we going to get that energy? How are we going to get the ATP? How are we going to get the NADH? Because what you're assuming is whenever you're in the fasting state, you're assuming that blood glucose is low, right? We don't have high enough blood glucose to seriously run on glycolysis, right? So we're going to have to find some alternative energy source. And really there are two energy sources, and those are lipids and amino acids. So whenever you're fasting, for instance, if you don't eat, like let's say you don't eat breakfast, you go throughout the day, and you don't eat anything, by the time you get to dinner time, you are seriously going to be running on lipids and amino acids. So basically, when you're not running on glucose, the percentage of energy that comes from amino acid metabolism is going to sharply rise, right? And as we said, when you're doing amino acid metabolism, you're producing a lot of ammonia, right? So you can imagine that if we're not supplying ourselves with glucose, in other words, our blood glucose is low, we're going to be shifting our metabolism to metabolize amino acids. And that's going to cause our ammonia levels in the cells to rise. And I hope that makes sense. Okay? Like I said, there's only one other condition in which you would normally see ammonia levels rise, and that's if you're eating a very, very, very high protein diet. So in that case, it's not that you're in the fasting state, I mean, you're eating. It's just that if the majority of your calories, the overwhelming majority, are coming from amino acids, then that's going to be what you're catabolizing. In other words, that would be like somebody having every meal of their day those protein shakes that you buy at the drugstore, assuming they don't have any carbs in them. If you're only running on amino acids, then you are by default going to be generating a lot of ammonia. So let's just think about that. So you're going to be to generate a lot of ammonia into metabolizing amino acids, and that's going to happen under two circumstances. Number one, if you're just eating a high-protein diet, but number two, if your blood glucose is low. In other words, your blood glucose is too low to constantly run glycolysis. So the generation of your ATP and mediation and so forth, all of those things are going to shift towards lipid catabolism and amino acid catabolism. So we'll sort of think of those going together. Okay? So, like I said, ammonia in large amounts is toxic to cells, so we have to have a way to deal with it. We have to have a way to get rid of the ammonia. And the way we do it is through this cycle called the urea cycle. Now, what I have written here at the top, when I copy and paste here, this is the reaction of carbonyl phosphate synthetase 1. Okay? Carbonyl phosphate synthetase 1 is a mitochondrial enzyme. Okay? And what this enzyme is going to do is it's going to activate ammonia. Okay? Ammonia won't just leave by itself. Okay? You have to activate it. And actually, the way we're going to get rid of it is by excreting it as urea. That's the way we're going to get rid of it. Okay? And this process of activating ammonia is actually pretty energetically expensive. As you can see right here, here's one ATP. We're going to do it in a different color. I'll do it in blue. Here's one ATP that we'll lose right here. And then here's the second one we'll lose in the third step. Okay? So carbonyl phosphate synthetase 1 is going to burn 2 ATP just to activate ammonia. And that by itself, based on our design, should tell you how important it is to get rid of this stuff. If you've got excess, you have to get rid of it. So the first step, bicarbonate, is going to attack the gamma phosphate ATP, and that's going to expel ADP as you're leaving it. And what that's going to do, as it says here, is going to generate a carbonic phosphoric acid anhydride. Okay? And this particular carbon right here that I'm circling, this carbon is actually very electrophilic. Okay? So, by the way, it's a carboxylic acid derivative, but it's still very electrophilic. It's got 3 oxygens on either side of it, which generates a huge partial positive charge in that carbon. So that, and by the way, you also have phosphate attached to it, which is a good leaving group. So ammonia will come and attack that carbon. And you'll get a nucleophilic acyl substitution with phosphate as your leaving group, and that's going to give you this molecule right here, which is carbonate. Although carbonate is not activated enough, so you have to activate it further with another ATP phosphate transfer. So this oxygen right here, this oxygen right here, is going to make nucleophilic acyl substitution on the gamma phosphate of another ATP, which ATP is your leaving group, and that's going to give you carbonoyl phosphate. Okay? This process that I'm talking about, this is also mitochondria. So just like glutamate dehydrogenase contaminates the mitochondria, so too is carbonyl phosphate synthetase 1. Okay? The mitochondrial enzyme, so the process of activating ammonia takes place in the mitochondria. Okay? And what we're going to find about the urea cycle is that the urea cycle is unique in the sense that it actually spans 2 cellular compartments. Number one, it spans the mitochondria, that's where the pathway begins and ends. But also, most of the cycle actually takes place in the cytosol. Okay? So let's talk about the cycle. And by the way, one thing I want you to do, like I said in the objectives, is we're going to generate a lot of things in amino acid catabolism that are not actually part of the main pathway. They're sort of just metabolites that come off here and there. And a lot of these metabolites have places here and there in the cell, whether it be in the cytosol or the mitochondria. And what I want you to do is I want you to think, where does this go in the cell? Where have I seen this before? Because knowing those kind of things is really going to help you out when you're trying to piece together the cell. Okay? We're actually going to run into one of those molecules in this pathway. Okay? So let's look at it. So the beginning of the pathway is when you start with ornithine. Okay, ornithine is a strange amino acid. It's not an amino acid that's found in proteins. In fact, if you were to look at the structure, it's actually one carbon, one methylene group short of lysine. So if you're drawing lysine, just shorten it by one methylene group. Okay? So that's ornithine. And ornithine is going to react with carbonyl phosphate. Okay? And the enzyme that does this is called ornithine transcarbamylase. Write that down. It's called ornithine transcarbamylase. Okay? Ornithine transcarbamylase, that's what they denote as 1 here. Okay? And what this enzyme is going to do is it's essentially going to transfer this component right here. It's going to transfer this component that's circling onto ornithine. And that's going to give you citrulline. Okay? Now this process, this ornithine transcarbamylase, this process occurs in the mitochondria. And once you generate citrulline, citrulline will then leave. Okay? Citrulline will exit the mitochondrial matrix and it will then go into the cytosol. So all this process down here, this is all cytosolic. Okay? So now citrulline is in the cytosol, and citrulline is going to act with another enzyme. And this enzyme is called argininosuccinate synthetase. Argininosuccinate synthetase. Okay? And the reason it's called a synthetase is because it's a condensation reaction that requires ATP. If you've seen my videos in the past, you will know the difference between synthases and synthetases. If you recall, synthetases were they were condensation reactions that require a nucleoside triphosphate. In the case of argininosuccinate synthetase, this particular synthetase requires ATP as the nucleoside triphosphate. And this particular enzyme is going to go through a very special intermediate, and that's shown here. It's the citrullyl AMP intermediate. Okay? What's the purpose of this? Well, what the enzyme is going to do is it's going to take citrulline and it's going to transfer the AMP group or the adenylate group onto this carbon right here. So this carbon right here, the circling, that's the carbon onto which the adenylate group is transferred. Why do we do that? Well, the reason we do that that is because we're activating citrulline. Okay? We're raising citrulline up in energy. That AMP group is not going to be on that molecule indefinitely. It's just the intermediate in the reaction. So we're activating citrulline so that we can ultimately transfer an aspartate molecule onto citrulline. So the first step of the mechanism is to transfer that adenylate group onto citrulline. The last half of the mechanism, which is labeled 2B near the bottom, is where we use an aspartate amino acid and we cleave off the adenylate and we generate argininosuccinate, thus the name argininosuccinate synthetase. So what have we seen so far? Well, when we did carbonyl phosphate synthetase 1, we burned 2 ATP. That's already energy expensive. But not only that, we had to burn a third one. So that third one is in the enzyme argininosuccinate synthetase. Okay, I hope that makes sense. Now what we're going to do is we're going to talk about the third enzyme. And the third enzyme is called argininosuccinate lyase. I'm going to abbreviate that. Argininosuccinate lyase. Another way you might also hear this enzyme referred to is argininosuccinase. Argininosuccinase. And I'm also going to tell you this because it's really important. Oftentimes when you see an aspartate attached to something and the very next enzyme is a lyase, oftentimes what that means is you're going to cleave off a fumarate. Okay? So whenever you see aspartate come on and the very next enzyme is a lyase, that's a good hint that the next substrate that comes off, or I should say the product that comes off, is fumarate. That's a very common motif in enzymes and amino acid metabolism and biosynthesis. Now, argininosuccinate lyase is going to produce arginine. So not only are we degrading we're not degrading, but we're getting rid of ammonia, but we're also seeing the biosynthesis of our first amino acid, that's arginine. This is the first biosynthesis, even though technically we're in the amino acid catabolism playlist. And even in the context of an amino acid catabolism chapter, you are going to see some biosynthetic reactions. This is actually how you biosynthesize arginine, is using the urea cycle. Okay, now remember what I said. I wanted you to think about, we're going to generate some metabolites in these pathways, and you've seen them before, at least you should have seen them before in your previous studies, and I want you to think what happens to them. Okay, so fumarate, give you a minute to pause the video, and I want you to see if you can figure out where you've seen that before. I'm assuming you'll have to have a go at it. And fumarate is something we saw in the TCA cycle, right? So what we can do with fumarate is we can put it into the TCA cycle, right? We can put it into the TCA cycle, okay? And then when we put it into the TCA cycle, what enzyme does it react with? Well, it reacts with fumarate hydratase. So once we react with fumarate hydratase, what do we get? On my mouth, when we react with fumarate hydratase, we're going to get L-malate, right? So L-malate looks like this. So through one reaction, we're going to get L-malate, right? And then, once we have L-malate, we're going to react that with what? With malate dehydrogenase, right? And in the process, we're going to use NAD, and we're going to get out what? NADH, right? And that's going to give us oxaloacetate, right? So what happened? Well, we ended up burning 3 ATPs just to get rid of one ammonia molecule, right? And that seems very energetically expensive, and it truly is. But because we generate these fumarate, and we can put that into the TCA cycle, where by the end of the cycle we'll get one NADH back, we take away just a little bit of that energy exhaustiveness, right? We take just a little bit of it away and reduce the amount of loss, right? But the fact that we're willing to waste so much energy to get rid of ammonia tells you exactly how important it really is. Okay, so this is our synthesis of arginine, okay? And in the very last step of the cycle, we're going to react with another enzyme, this is purple. This enzyme is called arginase. Arginase, but you get the point. Arginase is a hydrolase, and what it's going to do is it's going to hydrolyze off urea. So this right here, this molecule is urea. And urea, at least in humans, this is the way that we excrete ammonia. We can't just simply like any other amino acid, it's going to be in the L isomer. And when we generate one of these, then we can use a transporter to move it back into the mitochondria, and that's how we regenerate the cycle. So once again, we'll have another carbonyl phosphate waiting for us, and then that ornithine can react with it, again with ornithine transcarbamylase to make citrulline. Okay? So let's do a quick recap of what we've seen. Okay? We have many sources of ammonia in the cell, and most of them are going to be amino acid catabolic pathways. Okay? For instance, if we intake glutamine from the diet, or glutamate, or something that has an ammonia group on it, we can react it with enzymes that cleave off the ammonia, leaving nothing more than alpha-ketoglutarate left, right? In fact, one thing you might also think is the alpha-ketoglutarate can also go into the TCA cycle as well. That's something else we can say, okay? But the whole point is that, especially in high-protein diets, and in times when we're in starvation, fasting, when we have low blood glucose, a higher percentage of our energy is going to come from amino acid catabolism. As a result, we're going to have increased ammonia production, okay? The way we get rid of ammonia is first by activating it. And we saw through carbonyl phosphate synthetase 1, we have to burn 2 ATPs to get the carbonyl phosphate, a very energetically exhaustive process. This process, like glutamate dehydrogenase and glutaminase, occurs in the mitochondria, okay? And in the mitochondria, ornithine transcarbamylase can transfer this carbonate cycle takes place in the cytosol. Citrulline reacts with arginine succinate synthetase, and it transfers that adenylate group onto the carbon that's labeled in yellow. This activates citrulline so that you can transfer the aspartate amino acid onto it, generating arginine succinate. And by the way, something else we also should note about this reaction is the first part of it is going to cleave on pyrophosphate. And certainly if you've seen my videos on fatty acid activation, where we add fatty acyl-CoA synthetase, we also generate a pyrophosphate. And if you remember, we had an enzyme that reacted with inorganic pyrophosphate called inorganic pyrophosphatase. And what this enzyme did is it cleaved apart the pyrophosphate into two inorganic phosphates. And this reaction is associated with a very large negative delta G. That negative delta G that releases free energy, that exergonic reaction, is used to drive work in the cell. Okay, so we've generated arginine succinate, and now we're going to use arginine succinate lyase to cleave off fumarate, and we end up generating arginine. So that's the biosynthesis, at least the first one we've seen from the amino acids. Okay, and the fumarate can then go into the TCA cycle and react with fumarate hydratase to give us this. This is malate, right? And then malate dehydrogenase gives us oxaloacetate, completing the TCA cycle, and also in the process giving us 1 NADH. Okay, so when we're going throughout these pathways, just think about that. We're going to generate all sorts of metabolites in these processes. Just think about where they might go in the cell. So star fumarate, keep that in mind. And also keep in mind NADH and things like that. Okay, so we have arginine, and then to complete the cycle, which is going to occur in the cytosol, we're going to hydrolyze off urea, and that regenerates ornithine, which goes back into the mitochondria to reset the cycle. Okay, so I hope this video gave you a little bit of intuition on the urea cycle. See you in the next video. About the urea cycle. And to do that, what we're going to do is we're going to first talk very briefly about transaminases. And actually, in the next video, we're also going to talk about transaminases. We're going to talk about alanine aminotransferase. And also, what we're going to do to really solidify the urea cycle is talk about the aspartate arginine succinate shunt. We talked about generating fumarate. We talked about supplying arginine succinate synthetase with aspartate. How do we do that? We're going to answer that in this video. Welcome back. In the last video, we looked at the urea cycle, and we saw that the urea cycle is useful for eliminating ammonia from the body, especially in times of a high-protein diet, or when we're constantly catabolizing amino acids. Okay. And we're actually going to do a continuation of that in the last half of this video. But before we do that, we're going to talk about a really, really important topic. And by the way, this topic is important not only for amino acid metabolism, but it's also important in amino acid biosynthesis and nucleic acid biosynthesis. So you'll see this again and again and again, so it's good that you get it now. Okay, so let's say that I have this molecule right here. And if I ask you what functional group that is, you would tell me that it's a carbonyl, right? And let's say that I have some enzymatic pathway, but that pathway does not require a carbonyl. Instead, it requires this. Let's say that instead it requires an amine, right? So instead of requiring the carbonyl, it requires an amine. Well, it would be good and dandy if I had the amine, right? But instead I have the carbonyl. That's a problem, right? Because the pathway wants this guy, right? It wants the amine. Okay. Well, it turns out that there's a type of enzyme that can interconvert carbonyls and amines, okay? And it pains me to say this, but I'll say it anyways, just because it helps conceptualize what's happening, okay? It pains me to say this, but you can effectively think of these reactions as a substitution reaction between a carbonyl and an amine. Now, note that I'm not telling you that's what happens mechanistically. In fact, mechanistically, from an organic perspective, it's very, very different. It requires pyridoxal phosphate as a coenzyme. But effectively, when you're drawing reactions and you're trying to think of structures on your exam, this is what you can view it as. It's a substitution between a carbonyl and an amine. But where does the amine come from, right? So that would imply that you also have to start with another molecule that has to have an amine as well. You do. So let's say that I start with this with an R double prime and R triple prime. And let's say this has an amine on it, right? Well, if it's truly an effective substitution, then I can put this amine in here, and then I should get a carbonyl out of this, right? So what did we just see? Well, we just saw that a carbonyl was transformed into an amine, and an amine was transferred or transformed into a carbonyl, okay? The type of enzyme that catalyzes this reaction is called a transaminase. Sometimes they're called aminotransferases. But the key with transaminases is they're usually they're always interconverting carbonyls and amines. Okay? And one thing that's important to realize is most of the time, like 99% of the time, the pathways you're going to see, the carbonyl is a ketone. Sometimes you can be an aldehyde, but ordinarily it's going to be a ketone. And I believe, for the purposes of Leninger's Biochem 1 and 2, that textbook, 6th edition, I believe everything's a ketone. I might be wrong, but basically, the carbonyl is usually a ketone. It can be an aldehyde, but you're just saying it's a carbonyl, and it's going to be transformed into